we're finally to the ominous related rates. Related rates usually follow right on the heels of implicit differentiation, since you need implicit differentiation in order to solve them. But we need implicit differentiation in a little different way. Okay, we're used to looking at implicit differentiation as, xy squared plus x squared y is equal to 2, and then somebody says, hey, find dy dx, right? And it's related to that, no pun intended. We're looking more like x squared plus y squared is equal to z squared, and you need to find a different derivative besides dy dx, and I'll explain it here in just a second. Okay, so it's not quite as it's not the same thing as that, but it's just as straightforward. You just have to know what to look for. Now, this is obviously a representation of what we usually refer to as the Pythagorean theorem. If we're given a right triangle and we have sides x, y, and z, we know that they're related in terms of the sum of the squares of the legs is equal to the square of the hypotenuse. Okay, x squared plus y squared equals z squared. Now, I know it goes without saying, but I'm going to say it anyway. This shows you how the magnitudes of the sides are related. Now, if this triangle starts changing shape, but we know that it remains a right triangle, not only are the sides going to be related to each other, but the rate at which the sides change will also be related. Okay? So the rates of change will be related in a way similar to the sides, the magnitude of the sides being related, hence related rates. Okay? So if I want this, and all related rates, almost every single one of them, I can't think of a counterexample right now, almost every single one of them is with respect to time. So I'm not going to be differentiating with respect to x like I was up here when I was sort of given a sort of an equation in the abstract. I'm given an equation which governs a particular scenario, and I want to know if this starts changing, if x starts getting larger or smaller, how is it going to affect the hypotenuse, if the other leg stays constant, or you can think of a whole host of different ones. Let's say x and y are both increasing in rate. Let's say that they're both getting larger. How fast is z getting larger? Let's say x is getting larger but y starts shrinking. What happens to the rate at which z is changing? And so you can think of a whole host of different scenarios, but the rates are all related. And what we need to do is, since all of these relate to how fast something is changing with respect to time, the with respect to time tells us that we're going to be differentiating by the variable t. So we are actually going to be finding d dt of what is given to us, because we want to know how fast is x changing with respect to time, how fast is y changing with respect to time, and how fast is z changing with respect to time. Well, that becomes 2x dx dt plus 2y dy dt is equal to 2z dz dt. Okay? And then, of course, this simplifies into, the 2's, you can divide through by 2. But that tells you that if the sides are related in terms of their magnitude in this way, the rate at which they change magnitude, they're related in this way. Okay? So every single problem that we're going to be dealing with in terms of related rates, there will be some sort of equation that is the basis of that scenario, and we will be given information, okay, and we will need to use that information to answer the question that is provided. So let's go ahead and continue on here. Let me give you a scenario. Let's say, let's go ahead and just go to an example. This is a classic one right here. Let's look at number 11 right here. A ladder is 10 meters long and is leaning against a vertical wall with its other end on the ground. The top end of the ladder is sliding down the wall. When the top is 6 meters from the ground, it is sliding down at 2 meters per second. How fast is the bottom moving away from the wall at this instant? Okay. Now, I'm going to go ahead and I'm going to fold this piece of paper so we can try to keep that question in mind as we start constructing this. But I'm going to go ahead, and as much as I'm against method, there are a few methods that actually help us in terms of this particular type of problem. The first thing that you want to do is, insofar as it's possible, you want to draw the scenario. So step one is to draw the scenario. A ladder 10 meters long is leaning against a vertical wall. Okay? Well, you know, if we want to get out the ruler and we can go ahead and is leaning against a vertical wall, and you know, there's the ladder, you know, beep, 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 beep. Yeah, never claimed that I was an artist. The top end of the ladder is sliding down the wall. Well, here we actually, obviously when we draw a picture, it's a static sort of thing, right? We can't actually show the motion, but we can anticipate the motion. And what we want to do here is we want to actually designate variables for all of these, except for those things that are constant, okay? 10, okay, that's not z, that's 10. The length of the ladder is not changing. Does that make sense? It's not changing. Therefore, we don't designate a variable for it because the length of the ladder doesn't vary. It's constant. We need to go ahead and designate this distance right here, how far the base of the ladder is away from the wall, as x. And we need to designate how far the top of the ladder is from the floor as y. Okay? That is our picture. Now, you're going to be given several pieces of information. Okay? There is what I usually call given information, and that means things that are not going to change. Okay? And that, of course, is your z is not z, it's 10 meters, and we've already taken care of that by putting it in the drawing that we did. Now, the next piece of information, the top end of the ladder is sliding down the wall. Okay? When the top of the ladder, see that important word when right here, that tells you that you're not dealing with given information anymore. And for lack of a better word, I usually call this the conditional information. Okay? Now, that means that they're going to give you information that is always the case, and then they're going to give you information that is true at a specific instant. Okay? And at that instant, in that condition, there are certain things that are true. It says the top end is 6 meters from the ground. When the top end is 6 meters from the ground. So when y is equal to 6. Well, when y is equal to 6, okay, it is sliding down the wall at 2 meters per second. Well, sliding down the wall at 2 meters per second, that describes how fast y is changing, okay? So that is dy dt. But you have to be careful here because that actually describes y getting smaller, right? So if y is getting smaller, this is not 2 meters per second, it's negative 2 meters per second, okay? So the ladder is always 10 meters. Well, it goes slipping down, okay? And so as the ladder slides out this way, as the bottom slips away, the top is going to be slipping down, okay? So y is going to be getting smaller, x is going to be getting larger, okay? And of course, I have to go ahead and designate actually the question that's being asked. How fast is the bottom moving away from the wall at this instant? That is a question of dx dt. Okay? Well, this actually is, and I'm going to go ahead and slide the, I think we've read that enough times that we now know what's going on. Now, I know that it's going to be x squared plus y squared is equal to 10. This is a Pythagorean sort of relationship. Now I know that that means that I'm going to get 2x dx dt plus 2y dy dt is equal to 0. Now, I also know that when I have this, those 2's go bye-bye. And what I'm actually trying to solve for is this dx dt. Okay? Now, I have 4 unknowns, x, dx dt, y, dy dt. I have 2 of them, but I need 3 in order to solve for the 4th. But the conditional information that was given to me was only 2 pieces of information. But there is actually sort of a ghost or an implied piece of conditional information. If y is equal to 6 at a particular instant, and I know that z is always equal to 10, a 3, 4, 5 right triangle tells me that at that same instant, x is 8. Okay? So while this is part of the conditional, it is not part of the conditional that was explicitly given, and therefore I usually refer to it as my implied conditional information, or just my implied conditional, okay? And I'm only being a stickler about sort of the what I call things, because I'm going to continue to call them these things as we progress through these videos, through more and more examples. Now from here, it becomes very, very easy. All I have to do is plug in, because once I've plugged in, I need to evaluate this and solve for the thing that is still unknown at the particular point in time when that conditional information is true. So x is, of course, 8 meters, dx dt, and I'm going to go ahead and shove this term over to the other side, negative 6 meters times negative 2 meters per second. I don't know why I put the 2 in superscript, but you get the idea. And so what we have here is these negatives cancel out, these units cancel out, those 2 meters, and this is going to be 12 divided by 8, and therefore dx dt is going to be 12 divided by 8, which is 3/2 meters per second. Okay? Now notice that it's positive, and it should be, because dx dt is positive means x is getting larger, and if the bottom of that ladder is sliding away from the wall, x is indeed getting larger, okay? Now this is a classic example of a related rate question dealing with Pythagorean triangles, right triangles and Pythagorean theorem. So all that we've done is we've taken the information, marked out a picture, chronicled all of the information that's given to us, including the given, stuff that never changes, conditional information, things that describe the moment in time that I'm asked a question about, and then of course the question that I'm asked. I need to determine from all of this what geometric or some other, what equation governs this scenario. I need to differentiate it implicitly with respect to t. I need to plug in. If I'm missing any information, I need to go back to the conditional and see if there's any implied conditional information that I missed. And then I need to solve for what I'm asked to solve for. That's basically it, guys. That's how related rates run. But they do get rather complicated. I've walked through this one very, very slowly and deliberately because I wanted to basically highlight all of the things that are going on. I'm likely to go a little bit faster in the videos to come, especially as we get on. I don't know how many videos this is going to be. I'm basically going to continue to make related rates videos until I'm satisfied that y'all have an example of all of the ones that you're going to see. Now, while your teacher may not spend a whole lot of time on this, and that's her prerogative, I actually spent quite a bit of time on this. You may or may not wind up seeing one of these on the AP exam, but if you do, it'll be 1/6 of the free response, and I'd like you to really be able to do these rather well. Okay, so we'll go ahead and call it quits for this particular video since it's getting on towards about 16 minutes. But I will go ahead and get started on the next one. Bye.